Time for another chat. This is going to be on one of our last major topics. The hair there, let's go. There we go. All bundled up. Oh, was it 3 degrees below zero here or something? It was pretty cold this morning. So I got 6 layers on, but made it down here in one piece. Didn't freeze on the way, so all's good. So we're going to look at some related rates. We'll dive into it right now. So let's see. Get this off. Get a marker. Get another marker. See if we can see what I'm seeing. Let's bring the table back this way a little bit. Let's start with something we know or something that we're nascent understanding. There's another one of our words of the day, emerging understanding of the integrative process, the layering. So I got a circle with a radius of 1, and I'm going to layer some area. And I'm going to do it by, well, let's get a different, each time let's get a different color here. Yeah, I'm going to go around that circle, and that green represents a change in area from whatever the area was to whatever it is now. And if we break that critter apart right there, each of these dashes represents a, let's do it out here, a dr, a little change in the radius. And if I open it up, that's why these things are sometimes called wrapping functions, I get a length. And if you are giving it some thought, that length is 2 pi r. Right? And that width is dr. And if I keep adding up from 1 to 2, another layer. That one's a little bigger than the one before it. Another layer. That one's a little bigger than the one before it. Another layer. Oh, repetition's my friend. I got the markers in one hand now. Oh, I'm saving some time. Boy, oh boy. All right, let's cut to the chase. Let's get to there. Right? If I add up all of those and I do the integration, let's do it first off. One strip. One strip. I'm losing that marker already. One strip. Losing that marker. Oh my God. These things don't last that long. Let's see if I got something over here that can help us out. I was well prepared. Let's see what we got. Okay, let's hope that lasts for a while. Being red the rest of the way. Let's go. From 1 to 2, 2 pi r dr, we have a little bit of integration to do here. So this is the variable is r, so it's to the 1 right now. So it's going to become 2 pi r to the 2 divided by 2. And I think we can see that, we've got a circular relationship here. And we're looking at the change in area from 1 to 2. That's the area that, we're taking from 0 to 1 is taking out this area. And then from 0 to 2 is that, and the difference between the two is going to give us the area that we just generated. So we've got 4 pi r, 4 pi minus 1 pi, and so that's 3 pi area. 3 times 3.14 gives us a feeling for what we just generated. Okay, but let's think about how we really got concentric circles expanding. That brings to mind throwing a pebble into a pond. All right, so if we throw a pebble into a pond, then this radius is changing at a speed. This radius is based on time. How long does it take to get from here to here? Well, let's build a little table. Let's bring in a little bit of time here. And remember, right now we're looking at the change in area is 2 pi r dr. Right? Dr being that little change to the right, circumference. Looks like I'm playing tic-tac-toe. There we go. All right, so we throw a pebble into a pond. And so that's time. And we're going to watch how the radius change with respect to time. And then we're going to look at the change in area. And that's a statement here, which is pi r squared, right? Area equals pi r squared. So we're going to look at pi r squared. Boy. Oh, get another cup of coffee here, pi r squared. So let's say the time, tick tock, tick tock, tick tock. Oh, no, that's not time anymore. That's a video now. I wonder what I'm supposed to call that. Seconds, maybe? Look, 1, 2, 3 seconds, 4 seconds, 5 seconds, so on and so forth. But the radius changes in terms of, I think there's a function here that I'm going to create. Maybe you can see the pattern. Yeah, patterns are everything. And then I guess we got no area, and then we got a radius of 2, so we got our 4 pi, radius of 4, 16 pi, radius of 3, 6, radius 6, excuse me, 36 pi. Right, so then how would we find out how the area is changing with respect to time? dA, 2 pi r dr. You know, I actually think that with respect to time, yeah, I guess if we were going to approximate, we'd have to do something like get a calculator out and do 3.01 and double it, 6.02, and then square. I don't want to. Pi 6.02 squared, and we'd have to look at the change in y, change in time. Woo. Yeah, but it looks like there's a relationship between dr dt here. Oh, can you see what it is? Can you see what dr dt is? And if you said 2 to 1, you would be right. And if we wanted to look at this instant, then I guess the radius is 6. Now, I guess we could see how change in area is changing with respect to time. Visualize that pebble in that water. Okay, so this is what we're going to be diving into, and it's called related rates. I mean, the rate of change here is related to what's happening over here with your radius and your time. Okay, so first time we've talked about it, generally speaking, I don't worry too much about the first time you hear something, because I'm not sure the brain can process it quickly enough anyway. So you think about it. We come back tomorrow. We talk about it again. But let's actually do a problem, a little related rates problem. Let's go to Wally's World. Wally's World, I think, was a Chevy Chase film going back in time. Wally's World. Oh, yeah, we have a wall over here. We got a ladder leaning against the wall, and we're going to pull the bottom of the ladder out in that direction. And in that direction, we have the x-axis. So we're going to pull the ladder out and call that dx dt. And what I want to know is, what is dy dt? I want to know how fast that ladder is coming down the wall at any particular moment. I mean, there could be a moment where we don't want to be coming down so fast that we get hurt. We want to know when that is. Don't get on the ladder to begin with. All right, so hopefully we got ourselves a little Pythagorean relationship. If I tell you the ladder is 10 feet tall, 10 feet in length. All right, I'm picking that obviously because we're going to do some easy numbers here to start. All right, we got a 6, 8, 10 is a nice Pythagorean relationship. 36 and 64 equals 100. All right, so we're going to get there. But the first thing you do with these things, I don't know what I'm writing here or why, probably give myself some thoughts before we get there, is that we basically created a 10, an X, and a Y. And you always want to work there first before you even dive into some numbers. But we're going to find out when it's 6 feet, when the ladder is 6 feet away from the wall, at what rate is it coming down? Okay, and we're going to see that, and we know dx dt is 2 feet per second. We want to know at what we're looking for dy dt. It's always good to write these somewhere. Dy dt is what we're trying to find when x is 6 feet from the wall. So first thing we do is we think about it in the generic sense. And that's where we can see that x squared, y squared equals 10 squared. All right. And so that gives us our equation. x squared plus y squared equals 100. And I think I did a video that helped you see, hopefully, the numerics at work in a Pythagorean relationship. It's one of the earlier videos a couple weeks ago. Implicit differentiation, how the numbers work, right? And I'm hoping you're looking at those things because you're trying to get a deeper understanding of what's going on, not just a nominal, a trivial understanding. You actually have to have a feel for numbers in this discipline, and that's the way you get it. You explore. So I hope that video helped you explore a little bit the proportional relationship that's going on. As the x squared gets bigger, the y squared's got to get smaller. And there's a proportional relationship there, minus x over y. So go back to that. But if we were to talk about this, the geometric change, remember what the geometric change is for x squared. It's a new x and a new x with a dx and a dx, right? That's the geometric change. And if this was y, then it's a new y, a new length, just slightly bigger than the old one with a dy and a dy. And what you get is 2x dx plus 2y dy equals the constant 100. There it is. That's a constant. There's no change. So again, if you start to see that change right before your eyes, please see me. I know we're in class. A week from now, just stay after class for a little bit. We'll have a little chat. So that's 0. Okay. All right. But what did we introduce? We introduced something that's respect to time. So that means if I have something like 10 plus 20 equals 30, and I divide by 10, and I divide by 10, and I divide by 10, I get 1 plus 2 equals 3. Yeah, that's true. So if I divide by dt, if I divide by a little change in time, and I divide by a little change in time, that's algebraically correct. Now, I think I could divide by 2, just to make this quicker and easier. Divide by 2. What do I have? I have x dx dt plus y dy dt. And that brings us back to the pebble in the pond, right? Getting a feel for these things. And it's going to take a little while, equals 0. Now we go back and we say, okay, x is 6. All right, then 6 squared is 36. 10 squared is 100. So 100 minus 36 has to be over here on Wally's world, 64. So now I know I got a 6, 8, 10 triangle. So when x is 6, dx dt was given. It's 2 feet per second that way, which means that this is getting bigger. So this has got to get smaller. All right, so this y is 8, and there's our, I'll just say what? No, I got to say dy dt. dy dt, is here. I'll be done in 1 minute, Ada. Dy dt equals 0. And so we've got 12 going to the other side. So we got 8 dy dt equals minus 12, and there's our proportionality. So what is dy dt? Dy dt is minus 12 over 8, which is minus 4 over 3. Did I do that right? 4 goes in, that's 2, excuse me, 3. So minus 3 over 2. So the ladder is coming down the wall at 3 feet every 2 seconds. That's what that's saying. All right, so enough. I got to talk to Ada now. Truncated video. We'll talk on Monday.